Hello students, today's our topic is normal Zeeman effect. As we know that in vector atomic model, we consider that the electron have two type of motion. One, it is moving around the nucleus, where nucleus is situated at one of the focus of the elliptical orbital path, and one motion is our orbital motion, and the another motion which is possessed by our electron is our spin motion. In our normal Zeeman effect, we are not considering the spin angular momentum contribution in the splitting of light in the presence of magnetic field. In case of normal Zeeman effect, we are only considering the orbital motion, not considering the spin motion. In case of Zeeman effect, when the spectral line comes in the presence or passes through a magnetic field, then this line splits into two or into three components. It depends whether the spectral line is parallel to the applied magnetic field or whether the direction of the spectral line is perpendicular to the applied magnetic field. Hence, Zeeman effect is a phenomena of splitting of spectral line in the presence of magnetic field. It is of three types. One is known as normal Zeeman effect, another is known as anomalous Zeeman effect, and the third one is known as Paschen-Beck effect. In case of normal Zeeman effect, this applied magnetic field strength is very high. We are considering that high magnetic field is applied. And in case of normal Zeeman effect, the spin motion is not considered, only the orbital angular momentum is taken into picture. When the direction of applied magnetic field is parallel to the spectral line, then in the output we get two components of the spectral line. One component have frequency larger than the original spectral line, and the another component have frequency less by the same order as the other one has increased. The next one, the second line, increased with the same order frequency. These two components here are known as sigma components. But if the direction of the applied magnetic field and the direction of the spectral line are perpendicular to each other, then this spectral line, after passing through this perpendicular magnetic field, it is find out that this spectral line is splitted into the three components. If this is our original spectral line with no magnetic field, then this spectral line, after passing through a magnetic field which is perpendicular to the direction of this spectral line, then this spectral line is divided into three components. The middle one component is known as pi component, and the side components are known as sigma components. The pi component have same frequency as the original spectral line have, and the two components side by side of the pi component, one has a smaller frequency and another has a larger frequency by the same magnitude. As we know, the electron is moving in an orbit, and now in our case we are not considering the spin motion. The electron is moving in this orbit, and the shape of the orbit and the orientation of the orbit or the direction of the orbit depends upon its orbital quantum number. If this is the direction or this is the path in which the electron is moving in its orbit. We very well know that with the help of right hand thumb rule, by curling the fingers in the direction of the orbit, the right hand thumb will indicate the direction of our angular momentum. This electron have charge, and when this electron is moving in a closed loop, due to that an magnetic angular momentum is also produced, and in our case it is produced by orbital motion. This is our orbital magnetic momentum, which is represented here by mu L. In our vector atomic model, we very well know that the ratio of magnetic momentum to the ratio of mechanical momentum is given by E divided by 2 m naught, where E is the charge on an electron and m naught is the rest mass of an electron. When this electron, which is moving in this particular orbit, is placed in a magnetic field making an angle of theta with the angular momentum of this orbit, then we very well know that this electron, which is moving in this orbit, will starts to change its path by an angle of theta, and due to this change we will get different types of orbit. It depends on the number of orbital quantum number. If there are large number of orbital quantum number, we will get different orientations of angular momentum with respect to h. We studied this in when we have studied our different type of quantum numbers, where we find out that when a magnetic field is applied, then the angular momentum starts to move around this magnetic field, and the horizontal component is represented by magnetic orbital quantum number ml, and the value of ml and the value of theta depends upon the different values of our orbital quantum number L. If L is equal to 2, then we have ml is equal to from plus L to minus L, having all the integers in between them including 0. We get 5 different values of theta, that is the for L is equal to 2, we have 5 type of orientation of this orbit around the applied magnetic field. It means this single orbit will now, when magnetic field is applied, can be in 5 different directions. And here we will explain how this splitting of single orbit is happening when magnetic field is applied to a electron moving in an elliptical orbit. As the orbital magnetic momentum and mechanical angular momentum have a ratio of E divided by 2 m naught, and we very well know that this magnetic field will interact with this magnetic field produced by the motion, orbital motion of the electron. It means there is a change in frequency. When a moving electron comes in the contact with an applied magnetic field, then due to the magnetic force that is given by QV cross B, we very well know that the motion of the electron will increased by this force or maybe decreased by this force. It means the velocity can increase as well as can decrease. It depends in which direction the force is applied with the help of this applied magnetic field on this electron. And due to the change in velocity, we very well know that if the velocity will increase at 1 second or in a particular period of time, the number of rotation will increase. It means we are increasing the frequency of the electron moving in an orbital path. If this applied magnetic field is applying a force on this electron such that the velocity of the electron is decreasing, it means we are decreasing the time period of one revolution of the electron in its orbit. It means we are decreasing the time period. It means we are decreasing the frequency. Indirectly, if the velocity goes on increasing, the number of rotations goes on increasing, and if velocity goes on decreasing, the number of rotation goes on decreasing. Hence, there is an effect on the rotation number per second of the electron, and that physical quantity, very well known to you, is none other than frequency. Hence, due to the applied magnetic field, the electron which is moving in this path, when magnetic field is not applied, starts to move with different frequency in different path due to the force produced by this applied magnetic field. And this new angular frequency, let us consider, we are denoting here is with omega L. This is the known as frequency of Larmor's precession, as the term you very well know that we have already discussed about the Larmor precession in vector atomic model. And in our case, where H is the magnetic field, the Larmor precession is mathematically given as the ratio of the magnetic angular momentum to mechanical angular momentum into the intensity of the magnetic field. And from this ratio, we can substitute E divided by 2m0 times of H. It means this is the new frequency which come into picture when magnetic field H is applied to the electron which is moving in an orbital path. The new frequency will change the energy of the particle. If the frequency changes, then according to our formula, half of mv square, we will get half of m omega square r square. We will know that the kinetic energy will change, and if kinetic energy will change, the total energy of the particle will also change. And the change in the particle energy is given by, that is, omega L frequency, Larmor frequency, and into the projection of mechanical angular momentum about H. It means if this is the orbital motion of an electron, then with the right hand thumb rule, if we are considering the anticlockwise rotation, this will be the direction of our orbital angular momentum. And if we are considering that we are applying magnetic field in this direction, and these both vector quantities are making an angle of theta with each other, then the projection of mechanical angular momentum in the direction of H is given by, that is, PL cos of theta. Here we are considering this term. This term will change the energy of the particle also. As theta changes, the value of precession will change, and due to the change in the angular frequency, there is a change in the energy. Now let us consider. Now we will substitute the value of omega L and our mechanical angular momentum by classical assumptions. We very well know that PL is none another than L star H cross, and in case of classical mechanics L star is equal to L, and in case of quantum mechanics consideration we very well know that L star is equal to under root of L into L plus 1. So we very well know about the value of our angular momentum, and value of our Larmor frequency we already find out that it is given by Em naught divided by H. Hence we are aware how by how much amount our energy is changed, that is omega L into the projection of our angular momentum in the direction of the applied magnetic field, and it is given by 2m naught H into L star H cross cos theta, where H cross is our Planck's constant divided by 2 pi. Substituting this value we will have EHH divided by 4 pi m naught into L star cos theta, and by changing L star cos theta in terms of magnetic quantum number, ml is given as m, that is L star cos theta. So the change in energy in the case when magnetic field applied is H is given by this relation, and here the orbital motion is considered and spin motion is neglected. Let us consider an example to explain our normal Zeeman effect. Uh, let us consider the electron is moving in a principal in energy shell having n is equal to 2. We know when n is equal to 2, L have two values, one is 0 and another is 1. And if L is equal to 0 and 1, it means we have two sub levels. One is for L is equal to 0 and another is for L is equal to 1. If electron is moving in L is equal to 0 and it goes into L is equal to 1, it means there is an exchange of energy. And if it is moving in L is equal to 1 and it is come into L is equal to 0, it means again there is an exchange of energy. Let us consider the energy of the electron present in L is equal to 1 is considered as E2, and the electron which is present in L is equal to 0, let us consider it is represented by E1. And until now there is no magnetic field is applied, there is no H, there is no magnetic strength is applied, and if there is exchange of energy, electron in these two levels, let us consider the change of the energy in between these two levels is given by this term, that is energy minus energy is equal to H nu naught. Now what happens when magnetic field is applied? Let us consider now magnetic field is applied and magnetic field have strength H. We know that when H is applied, this electron will change with some sort of energy, and this is the amount of energy by which the energy of this electron will change. So that happens to this electron. The energy of this electron will also change with the value, with the magnitude of this amount. It means now the new energy of the second electron, let us consider it is our E2 dash. It is given by the old energy plus new energy, and the new energy or the change in energy or the change in increase in energy in our case is given by this amount. And That happened to the second electron also, that is moving with energy E1. Now it is moving with energy E1 dash, and the energy will change by an amount EHH upon 4 pi m naught. Here we are taking it as ml dash, because in both the cases here L is equal to 1. Let us consider this is L, this is L dash, or let us consider this is L or this is L dash. We are indicating different values of L with different rotation, one with L and another with L dash. Now we will differentiate and find out what will be the change in energy. If we find out change in energy, then left hand side minus left hand side, energy minus energy comes out to be energy, and energy minus energy, we very well know that it is taken as h nu naught, and in this case all the terms are constant or common, EHH upon 4 pi m naught, and when we subtract this term from this, we will get ml minus ml dash, and there is we can take common or cancel out our Planck's constant, and we will have this E h upon 4 pi m naught, and quantum number minus quantum number, again there is a change in quantum number, and here we are representing it with by delta m.